Okay, so here's our final question for this unit. Again, electric potential actually has some of this. It's a lot simpler than the field and force because energy is a scalar. So we don't care about the direction, just care about the distance, how far it is. So this question says, calculate the electric potential at points A and B in the figure. And remember, potential is scalar. All right, so what we're going to do is say, okay, at A, we have to just find the potential of each one separately and just add them together. So if we want to do it at A, we say, okay, VA is just going to be the potential caused by the positive 50 microcoulombs plus the potential caused by the negative 50 microcoulombs. So you got VA is equal to 9.0 times 10 to the 9 newtons meter squared per coulomb squared times 50 microcoulombs, and it is a distance of 0.30 meters away. We're going to add to that the 9.0 times 10 to the 9 newtons meter squared per coulomb squared, and it's negative 50 microcoulombs, and that one is a distance of 0.60 meters away. So you multiply it through to get a value of 7.5 times 10 to the 5 volts. At B, if you plug it through, because they're actually the same distance away, they're both 0.4 centimeters away, we end up with 9 times 10 to the 9 times 50 divided by 0.4 plus the same thing but negative, so you actually end up with just 0 volts. So very easy. The question might be like, oh, now we might have a second part of the question saying how much energy is required to move a charge from point A to point B. So for that one, all we need to do is say, okay, first of all, we need to know what is our change in energy. So change in potential, I mean. So we know work is just Q times that VAB. So how much energy do you get from A to B? Sometimes are we going from A to B, or are we going from B to A? So for example, we want to go to A to B. First I'll say, what type of charge are we going there? Trying to get from A to B. So maybe we're trying to move an electron from A to B. So if we want to do that, we say, okay, electron is negative 1.602 times 10 to the negative 19 coulombs of charge. And we're going to try to go to A to B, so we have our final location is 0 volts minus the 7.5 times 10 to the 5 volts. And we plug that in, we got 1.602, secondly negative 19, multiplied by negative 7.5 times 10 to the 5. We get a value of 1.2 times 10 to the negative 13 joules of energy. Now I just think about our numbers saying, should it be positive or should it be negative? And yes, it should be a positive number because a negative charge does not want to get closer to a negative charge. So if we have, we're at A, we have that electron that's out here. Electron wants to move away from negative and wants to go towards positive. But by moving here, we have to add energy. We have to apply some energy to move that electron to a point that's closer to the negative charge. So we have to put energy into it. Now this doesn't matter how complicated you get. You can get some interesting questions where you have, say, let's say we have like a sphere or a circle, and we have a ring of charges around it. The question might be, what is the potential right there, right in the middle? And all we have to do for that is just add up all of the individual charges and the distance away. So in this case, even if it's a circle, they're all the same. So it's gonna, if you just calculate one, the electric potential for one of them, multiply by 8 in this scenario, you get a and then you have your electric potential value, which is 8 times whatever that V value was. And direction doesn't matter. Again, field does make a big difference though. So electric field, in this case, if I had that scenario and I had a bunch of positive charges around it, And I said, what is the electric field in this middle area? Electric field there is actually 0, because what's happening in that scenario, if you just picture this one's creating electric field away from it, the other one's creating electric field away from it, now the other one's creating electric field away and away. They're all just canceling each other out. So electric field is 0, but the electric potential is actually a very large number.